Okay. So last week we stopped here at, for example, 4, chapter 2. So we have discussed Gauss law, and what is the implication of conservative field, and due to the fact that if this is a conservative field, so from any point, let's say from any point from point A, let's say we bring a point charge from position A. So to from position A to position B, and then back to position A. So it will basically indicates there's no work done, because if the field is static, it is electrostatic. That means at any point here from T, let's say I already put a marking, which is this point and this point. All right. So the electric field magnitude at this point and this point, it will maintain. It will be maintained regardless the time lapses, regardless the time how I mean how much duration there it has passed. So the electric field should be the same at this point here and at this point here. Of course, the magnitude here and the magnitude here is different because they're different points. So since we knew that the electric field is it is dependent on space, dependent on the dimensional space, x, y, z. Um, Therefore, these 2 points, the magnitude is different, and same goes for the direction. Yeah. So here, I did briefly mention about uh, the implication of this and about Kirchhoff law, right? So about Kirchhoff law. So from here basically we see that this is Kirchhoff law basically. If you look at this, so because Kirchhoff law states that um, the potential in a closed loop, if we sum all the potential in the closed loop, is basically zero. So of course we have only 3 lines. So assuming that this is one line here, from here to here there's L1, and from here to here is L2, and from here to here is L3, and of course we can separate this into different paths. So the integral, this integral here, so it tells us that I can expand this as E1 L1, for example, plus E1 E2 EL2 plus EL3, and so on. Yeah. So I can break it out into different path, because the path is arbitrary. Okay, the path is arbitrary, and the electric field, it is at different direction. Yeah, it is at a different direction, and so on up until E times Ln. So it's equals to 0. And here we see that E times L is basically, this is basically V1 plus V2 plus V3 plus up until Vn, which is equals to 0. So here we have a special case which you already know what is Kirchhoff law. So Kirchhoff voltage law, right? This is Kirchhoff voltage law. So that is the implication. So now for this last part, calculate the work done in moving 10 microcoulomb charge from point A to B. Okay, so we are going to use I mean, we can calculate V, this V, okay, the VA and VB, okay, VA and VB directly. So which is the easier part? So first we can calculate V of A. Okay. Then okay, so R squared is 1, right? Sine theta is 30 degrees. And phi is 120 degrees. So which is equals to, so it's negative 2.5. Okay. So potential difference to 2.8125 volts. Yeah. Okay. So you said moving, calculate the work done, right? So we have calculated the watts, the potential difference. Therefore, the work done is watt per charge, right? Sorry, watt times charge. Sorry, Q times V. Yep, Q times V. Yep, sorry. So it's 10 times 10 to the power negative 6. Just make sure it's 10 microcoulomb. Okay, times this watts. So we have 28.125 microjoule. Yeah, microjoule. So okay, there's two ways. As I said, this is the easy way, and another way is we have to integrate E. So I'm going to show you two ways. So we are going to integrate E with respect to the path taken. So I'm going to use this. I'm going to use the E value. So here is another way of calculating the potential. So here we knew that potential is negative integral from A to B of E dl. So bear in mind the differential path length of dl in spherical coordinates is dr r cap plus r sine theta d phi, sorry, is r d theta, sorry, um, theta cap plus r sine theta d phi cap. Yeah. So if you perform the dot product, if you perform the dot product, E the vector E dot dl or for the differential path length for spherical coordinates. So the r cap dot product with r cap, so the rest is zero, so only dr. And then we have this is a minus, so this is a plus then. Yep. Plus 10 over r cap cos theta cos phi. So this r squared d theta. And lastly, 10 over r cap. So this multiply this is r squared sine squared phi sine theta d phi. Sorry, sine phi only. So no, not sine squared, phi. Sine theta d phi. So here we can see each of this term. So if we multiply, as I said, if we multiply E, the electric field that we that we have obtained last week, based on the potential. So if you perform a dot product with the length dl here, then the result of this, we can see that each of the integral, each of this integral here is independent. Is only one variable of interest. Okay, is only one variable of interest. Okay, so how are we going to suppose? So the thing is, how are we going to suppose? What is the limit for each one of this, right? So the first one is supposed to be what is fixed and what is variable. So the limits, the first one is 1 to 2. 1 to 4, sorry. Because A is 1, the radius is 1 to 4, right? So that's the variable. So theta will be fixed at 30 degrees. And phi is fixed at 120 degrees. So theta will be fixed at 30 degrees and phi is fixed at 120 degrees. So first we take the path from R to here. That means R will I mean the let's say assuming that point charge will move from position 1 to 4 in radial direction. This at a fixed plane of 30 degrees and 120 degrees. And eventually, so how about this? So we are integrating with respect to d theta, right? With respect to d theta. So now, so that means this is from 30 degrees to 90 degrees. So what is fixed here? Fixed is 4. So because we are in this position, we are already at position 4. And then theta is the variable of interest that we want to integrate. Phi is fixed at 120 degrees. And when you reach the third integral, so what is the limit? So the variable of interest is d phi, which is from 60 degrees to 120 degrees. R is still fixed at the plane 4. So sine theta, it is fixed at 90 degrees. And sine phi is variable. Yep. So I'll come again. So first, I bring a point charge at this point, starting from this point, 30 degrees, 20 degrees. I'm going to fix at the plane of 30 degrees and at the plane of theta, fixed plane of theta, which is 30 degrees, fixed plane of 120 degrees. Yeah. So I'm going to bring A to B. Wait, just let me think of how way that I can show it in a diagram way. Okay, let me just draw it here a bit. Just sorry, maybe I write wrongly. Ah, yeah, correct. I write it in a different way, sorry. Yep. Yep, you're right. It's 120. Yep. So so let's say this point A, which is somewhere, for example, 130 degrees. It's somewhere around here, A. Okay. So 130 degrees, 120 degrees. So at a fixed plane of theta and phi. So I'm going to move it to A. Let's say I'm going to move it to B prime. Yeah. So A to B. So let's say a B prime. D. Okay. Let's say B prime is 430 degrees, 120 degrees. Sorry, I think this is not good. Just give me a second. I redraw again. I thought I can keep with the equation, but never mind. So let's say this A position A1, 30 degrees, 120 degrees. So to point B prime, let's say B prime is somewhere here, 430 degrees, 120 degrees. So from here to here, okay. And then I move up to 90 degrees. So now to B double prime, say here it will be, so B double prime is 430 degrees, sorry, 90 degrees, 120 degrees. Okay. So I move up here. Okay. And finally to B, which is 490 degrees, 60 degrees. So so one changes at a time. So change of R, change of theta, change of phi. So therefore, excuse me. So so as I said, so one changes at a time. So therefore I write the variable change from R for radial changes from 1 to 4, fixed at 30 degrees, 120 degrees. And after that, for the second integral is the changes of theta, which is from 30 degrees to 90 degrees. So where now the position is at position 4, R equals to 4. And the plane, the other value, the other plane is fixed at 120 degrees. And the third integral that represent um, B prime. Okay, starting from B prime, that means the changes is from 120 degrees to 60 degrees. So from B double prime to B. So, which is the third integral. So fix r equals to 4 and sine phi is the variable of interest. Theta fixed at 90 degrees. So now, the first integral will be 20. Okay, this will be, sorry, I have to go back and forth a little bit. So it's 10 r squared from 0, sorry, from 1 to 4. So sine 30 cos 120. And minus integrate of cos theta is sine theta from 30 degrees to 90 degrees, and then multiply with, oops, sorry, 10 divided by 16 cos 120 degrees. Okay. Um, cos 120 degrees. And lastly is, so integrate sine, integrate, so integrate sine phi is cos, negative cos. So sine 90 degrees. So it's sine 90 degrees. Okay. So let's calculate each one of them. So please let me know. I might be wrong. Okay. I might press something wrong. Okay. So altogether is 2.81255. So therefore, um, W is Q times V. Again, we have 28.1255 microjoule. Yeah. Yep. 1255 microjoule. So it's the same. Is you get the same answer basically. Yeah. Both approach. So here we demonstrate two alternate one alternative one alternative method, which is using the potential, which is given potential directly. Another one, if let's say we do not have potential, then we only have electric field, then we still can calculate what is the work done. um, if let's say we are bringing a point charge that following a certain path under the under the influence of this electric field, then that is the required work done from bringing from a certain point A to a certain point B. So yep. So that's the method of calculating work done. So one is using potential, another one is using electric field. So of course my steps here first is calculating V, but I can straight away calculate W by multiplying Q inside, right? By multiplying Q inside, but it will be, it's a bit convoluted. So I just trying to show you, by right, in actual fact, we are still calculating V, but um, explicitly I have shown you that, of course, electric field, I calculate the potential, and then after that, from the potential itself, I multiply with the charge. That is the defined work done, right? Of bringing the point charge from point A to point B. So on the other hand is the potential, which is the given in the questions. So I just plug in the value for point A, what is the potential at point A and what is the potential at point B. I find the potential difference and I multiply, basically I just multiply the Q to get the work done. So bringing from point A to point B. So yeah, so that's it. Okay, for this chapter. So before we move on, so bear in mind the work done. So the energy is basically represented by the charge multiply the potential difference of bringing from one point to the other point. Okay. So we are going to chapter 3 now. So before we end this chapter, is there anything that you would like to clarify regarding this topic? Sorry, Kaibun, what do you mean all the same value? The three components all the same value, which Which are you referring to? I don't really understand your question. Which one you're referring to? Second method, the final answer for each component, from each component. Second method, final answer for each component. Uh-huh. You mean you get the same value as mine or what? Okay. Okay. That clarify. Okay. Thank you. Okay, so we move on to, so there's, what about others? There's no questions? Okay. Um, so we go to the next chapter. So now we are studying under, for the material property. What is the, for the material property under the influence of electric field and also the energy density. So first, um, we come back a little bit on the flux line. So basically the electric field, which is represented by the solid line, and the dotted square. The dotted square is defined. It is defined as the equal potential surface. So what does it mean by equal potential surface? So assuming that this is a point charge Q. So for point charge Q, the potential can be calculated directly. I mean, based on what we have learned in the last chapter. So the potential contributed by a point charge is given as Q divided by 4 pi epsilon naught R. Yeah. So the each of these dotted lines is the same potential. It is the same potential. So it means that, um, this circle, let's say they have a certain, so this circle here which I'm going to color it with different color. So I'm going to circle with different color. Okay. So each of, let's say, the red circle, the potential can be written as V1, let's say, is Q over 4 pi epsilon naught R1. Okay. And the blue and the potential V2 is divided by R2, and the potential at the green circle is Q divided by 4 pi epsilon naught R3. Okay. So R1 is the inner circle, R2 is which is greater than R1, and R3 is the largest circle. So this, which is, in other words, which is R1 is less than R2, less than R3. And R2 is less than R3. Okay. So the larger the R, the smaller the smaller value of the potential. So each of this point, let's say for the red circle, each point on the red circle represent the same potential. Yeah, because it is the same radius, right? From the point charge. So same goes for blue, for the blue circle. So each of the point that lie on the blue circle have the same potential value, because the distance from the point charge is the same for the blue circle, and the same argument goes for the green circle. So therefore, this represent the equal potential surface, and if we superimpose the the potential surface, it is as so because this is seen as like a two-dimensional circle, but in fact it is a three-dimensional sphere, right? So imagine that each of these circle drawn represent by a three-dimensional sphere, yeah, enclosing the charge. And if the electric field, we knew that the point charge, the electric field direction, it is perpendicular to this to this spherical surface. So therefore, the equal potential surface and the direction of electric field, so it is perpendicular. That means the electric field, it is perpendicular at any point, of all the equal potential surface, the direction. So the direction of E, it is perpendicular to any point. So let's say here, so it is perpendicular here, here, and here. Okay. So now, um, so imagine you have, so we have encountered, I mean, we have talked about what is surface charge density. Basically, we have encountered most of the continuous charge distribution. So we have talked about surface charge density, we have talked about line charge density, we have talked about volume charge density. So basically, it's a distribution of charge that take up the space. So if it's a surface, then you take the charge distribution will take up the surface. If it is over a line, then the charge distribution is distributed over a line, and it's a volume, then the charge distribution is going to distribute over a volume. So, but however, um, leading up to, I mean, there's some unanswered question. I'm not sure you thought about it. So so we talk about, okay, let's say for example a volume charge distribution. What holds that charge distribution? What holds that charge distribution? So does it going to be stay forever in that distribution form, a spherical distribution form? Let's say, for example, a spherical volume charge distribution. Is it going to maintain that distribution? So before we answer that, so let's look at um, a simple scenario of how are we going to calculate. So assuming that first there is no, I mean, in this yellow region, in this yellow space, there is no charge. Initially, there is no charge. Yeah, there's no charge. And we bring Q1, charge Q1, a point charge at a point charge Q1 from infinity to position 1. Okay. So there's no work done. Basically, there's no work done transferring Q1 to this space, because in this space here, in this space, yellow region space, there's no charge. So originally Q1 is initially there's no charge distribution over this yellow region, and therefore when we bring Q1 to this yellow region, there's no work done against any electric field. So there's no electric field in space initially. So therefore Q1, no work done to bring it to P1. So now Q1 is at P1. Okay. So Q1 is at P1. All right. So when we bring Q2 from infinity, let's say, when we bring Q2 from infinity and put it in point 2, we want to place it in point 2. So there is some kind of work done, right? There's some kind of work done required to bring the charge of Q2 to position 2, P2, because there's some kind of work done, because we have electric field contributed by Q1, right? So there's a potential, there's some kind of electric field that we have to overcome, uh, contributed by Q1 at position P1, and there's a work done to overcome uh, the electric field coming from Q1. So now we have two charge, P1 and P2. P1, P2. And again, if we try to bring a charge Q3, so now the charge Q3 have to overcome the electric field contributed by P1 and the electric field contributed by P2. So again, uh, going back to if we want to talk about work done, going back to the equal potential surface, the discussion of equal potential surface here. So in space, there are many equal potential surface, contributed by charge Q1, point charge Q1, and point charge Q2. So coming from, let's say, the potential surface is like this. So this is the potential surface, let's say, just for example. Okay. So from Q1, from Q3, from infinity, reach overcome, passing through this equal potential require work done, right? So this equal potential surface is the contribution by both Q1 and Q2 in this position, P1 and P2 respectively. So the overall work done is then The overall work done is the work done bringing a charge of Q2 multiply the potential contributed by Q1 and bring the charge of Q3. So the work done on Q3 is to overcome uh, the is the work done to overcome the electric field, and therefore the potential contributed by Q2 and Q1. So that's the total work done in assembling this 3-point charge. Yeah. So that's the total work done in assembling this 3-point charge. So assuming that at this position, P1, P2, and P3, this position here, so that means they stay put. Yeah. So it won't move anymore. So we call that at this position, Q1, Q2, and Q3 achieve electrostatic equilibrium. So electrostatically, it is equilibrium. So that means the force that the experienced by each of them when they are in vicinity at the neighboring position, at this neighboring position, the force experienced by P1, P2, and P3 is going to be zero, the net force. So therefore, we call this the position is in electrostatic equilibrium. So now I'm giving you some idea, some initial idea why the surface charge density or volume charge density. So it will holds, yeah, as long as the equilibrium position, the electrostatic equilibrium is achieved. So it will holds that distribution. And come back to our discussion. So the total work done of bringing charge, all the charge Q1, Q2, and Q3, that's the total charge. However, if we assume that we bring charge Q3 first, if we bring charge Q3 first, okay, if we bring charge Q3 first, instead of bringing charge Q1, so now assuming that initially charge Q3 is brought into the position of P3 first, then only charge Q2, then only charge Q1. Okay. So, all right. So position, so 1 plus 2. So we have the same energy, twice the same energy on the left hand side, because 1 plus 2, twice the energy on the left hand side. And here is basically this potential here is basically contributed by position 1, position 2, and 3 of the point charge, and Q2 is the position of 1 and 3. And similarly, for the potential here is 1 and 2. Okay. So here we can say that, okay, the sum of this potential. So since this is a scalar, so the sum of this potential, it is, we can say that is V1, the total is V1, V2, and V3. And so the formulation here is therefore half of the work done bringing charge Q1, the work done bringing charge Q2, and the work done bringing charge Q3. So half of it. So this value, this product here, what is the implication of this? Is basically, of course, we are talking. I mean, I'm giving you an example from point charge of view. So uh, this value here is actually signify the average of work done, basically. So if you extend to n charges, so if you extend to n charges, is going to be Q1 V1, Q2 V2, Q3 V3, Q4 V4, and Q4 VN, QN VN, and up until n points. Yeah. So it's basically the average of all the work bringing point charge Q1, Q2, Q3, and Q4 up until Qn. So this is discrete. So I mean, this formulation is discrete. This formulation here is discrete. And the very same idea when I discuss about in chapter 1, when I said about uh, if this if the if the charge if let's say the charge if the charge distribution is going to be over a line, distribute over a line, and more is going to infinite. If let's say this n tends to infinity, if this n tends to infinity, and therefore the very same idea that I mentioned, this is going to be a continuous charge distribution, and therefore it will involve integral. So basically, this integral sign represents the sum of all energy of bringing all the charges into a specific region, okay, of or accumulating all these charges. So that's the energy acquired to achieve that. So okay, um, so these three representation for energy density, for line charge, surface charge, and volume charge. So this should be I would say, I mean, this is quite straightforward. So here is I mean, everything is multiplied by V. Of course, this term and this term here, the product of this term and this term represent the charge, a point charge in the charge distribution. And this is also the point charge distribution. Okay. So if we integrate over a line, over a surface, and over a volume. Okay. So the subsequent derivation here, I do not want to go through this. So it's a bit complicated. So I don't want to go through this with you. So I will use another approach, yeah, to explain, especially. So especially we want to find what is the volume, where's the energy density. So when we talk about energy density, so normally it is related to uh, the energy per unit volume. So it is more of these are the focus normally. So as I said, the subsequent the subsequent derivation of obtaining the energy density, which is this point here, is a bit convoluted, and I don't think it is important for you to know this or memorize this. So I'm going to give you I'm going to provide you a more simpler approach, of how can we obtain the energy density expression. So this energy, this is not energy density yet. This the energy of the overall, the energy of assembling the overall charge density. So for a continuous charge distribution. So imagining now, let's say we have a sphere. So let's say we have a sphere. Okay. Sorry about that. Um, so assume that I have a spherical charge density. Okay, I have a spherical charge density. So the E, so that means the charge distribution is the entire sphere, the charge distribution. So the so let's say the shaded region is the charge distribution. So it's going to be the entire sphere. And now say on the surface, on this surface here of this, let's say I pick up an arbitrary surface. Let's say I pick out an arbitrary surface here. Okay. So this arbitrary surface, let's say the area of this arbitrary surface is A. Yeah. Let's say dA. Okay. Okay. If let's it is being stated there. Okay. So say that this region here, all the charge, all the charge distribution over this region is static. Yeah. It is static. Yeah. The entire charge distribution is static. Okay, they have achieved electrostatic equilibrium, and let's say now, so it's not going to move about around. I mean, it's not going to move about the theta direction or the phi direction or the r direction. Okay, so it has achieved, as I said, it has achieved electrostatic equilibrium, and what would be let's say, what would be the electric field at this, uh, at, 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 at the proximity of this surface. So it means that, so imagine now I have this, so I'm just redraw this area. So this area here is dA. Okay. So for for proximity distance from this charge distribution, from a proximity distance from this charge distribution, So assuming that at this point here, okay, at this reference point, the charge distribution is going to be infinite. Okay, it's going to be infinite. Okay, and what would be, let's say, um, the charge distribution of this dA, this is sigma or rho, yeah. So let's say I put a sigma as coulomb per meter square, right? So what would be the what would be the electric field at this point of interest? So what is the expression of this electric field here? So as I said, the charge distribution is a shaded area. So now I redraw this. Okay. So I say that, okay, at this point here, which is close to this shaded area. So the from this reference point, this can be assumed, the charge distribution can be assumed, and can be assumed an infinite charge distribution. So we have learned this in Coulomb's law in chapter 1. So the E field, if so assuming that this is free space, it is in free space. So epsilon naught outside everywhere. So except here there's a volume charge distribution. So I'm just saying on this surface here. So the electric field can be written as, let's say, sigma divided by 2 epsilon naught n cap, right? So am I right? You can check back chapter 1. So the electric field at this proximity point, so assuming that I have a surface charge density, okay, of this shaded region, there is some kind of surface charge density. All right. So the electric field is this, right? From what we have learned for Gauss' law and also as for Coulomb's law. So let me bring you back. So for Gauss' law, we just ended. So by using Gauss' law for infinite charge distribution, E, right? For E is 2 epsilon. Yep. So sigma now, in my case, sigma now is my surface charge density for this area. Okay. So in fact, so the E field, uh, one is pointing up in the normal direction to this surface. So basically, if we talk about sphere, it's going to be radially outwards, but it is still perpendicular to this small area. And if let's say if I have an electric field up, because this is a surface charge density, it should be also down, right? It should be also down. So in the same direction, right? So now, so I want to I want to express the force. I want to express the force for experienced by this surface. So if let's say I want to express the force experienced by this surface, how should I write this? The force experienced by this differential surface dA. How should I write it? So I want you to try for a while. I want you to think for a while. Okay. So of course we can obviously write that dF. So it's the differential force experienced by this differential surface, which is E times dq, right? So I have sigma over 2 epsilon naught multiply sigma times dA. So which is sigma square over 2 epsilon naught dA. So that is the force experienced uh, by this surface charge distribution. So therefore, from this part here, I can write the force per unit area, the force per unit area. Okay, force per unit area. Okay, and this is the force per unit area, and we are about there. We are about there to. I mean, we are about there to find out what is the energy. What would be the energy or energy density? Okay, so force per unit area. So if I multiply with some kind of distance, so let's say I'm going to compress it a very small. I'm going to compress it to. So you give me a second here. Okay, so the dotted lines is the distance of the surface of the surface move from the outer surface move, right? We are trying to compress it everything. So this is the distance, say some distance, dl distance, yeah, some small minor distance. So if let's say we're trying to compress it a little bit, so what would be the required work to against this force? So given that the differential, I mean the force per unit area is given, and if I multiply dl, okay, if I multiply dl, so let me just erase this a little bit. So if I multiply dl both sides, um, so if I want to change it as, if I want to change this as volume, so I can make it as, because this is an area, so this distance here, if I multiply dl, so this is going to be, so this is going to be the differential work over dv, right? The differential work over dv, which is sigma square over 2 epsilon naught square. So this represent the energy density. This represent the energy density per unit volume, which is which what we have here. Okay, so this is not explicit, as you can see. This is not explicit, and we can always represent the points. I mean, this expression here, the points. I mean, for sigma square, in terms of E and D, right? So it is, you can always express as E and D. Sorry, give me a second. It's raining heavily outside. Give me a second. All right. Okay, sorry about that. So as I said, the expression given here, we can easily express this as, in terms of E and D, right? So E is given as so this is our constitutive relation between the charge density, elect the electric field density D, the electric field density D, and also the electric field. So this is the constitutive relation, and of course sigma here. Um, we can also you can also express this in terms of the E field, in terms of the E field and the D field, right? So this is going to be if let's say I'm going to express this E in terms of E, so this is going to be half epsilon naught E square, right? And sorry, there is no more n cap here, because when we talk about when we express as energy, there's no more direction, because energy there's no vector, yeah? Energy there's no vector. So energy there's no vector. And similarly, because as I said, the constitutive relation is um, epsilon naught E. So this is also D times E, right? So we have the same energy density. So we have the same energy density coming from this. I mean, this is. I mean, mathematically, this is a bit heavy, as I said. So that's why I'm not going to go through with you. But I'm trying to explain it to you that how this energy density can be obtained just by some simple deduction, using some simple deduction using spherical volume charge density. So what we want to do is first we establish what is the force per unit area experienced at the surface of the charge density. So we have established that. And from there we can establish what is the force per unit area, and subsequently changing the force per unit area as the energy density. So by multiplying dl, so which represent compressing the whole charge, compressing, I mean, I'm going to compress this charge density. I'm going to compress this charge density at the distance at a small gap of dl. So what I modify here is just at the denominator of the at the denominator I just multiply dl, and at the numerator I multiply dl, and the denominator I multiply dl. So the differential force multiply a small distance, so that represent the the work done, and the the differential area multiply the small gap here, the distance, can be represented by the volume. So we have the energy density. So I have already show you. So this is the energy density, and this is the, I mean, this is what is important now, in particular. So we can always reverse this. I mean, we can always reverse this to, I mean, not say reverse. So from this expression here, we can always go back to the integral. We can always go back to the integral equation as previous, yeah, as previously. So we can always go back to the integral equations. Okay. All right. Let's try one example. So 3-point charge is located at 0, 0, 0, 1, 1, 0, 0, and each of these point charge, there is -1 nanocoulomb, 4 nanocoulomb, and 3 nanocoulomb. So assuming the first, so we, uh, I'm going to use the understanding. So I don't like I don't like to use like directly the formula like this. So first, initially, so Q1, so the energy to bring point charge 1 is 0. Yeah, the energy to bring point charge -1 nanocoulomb is 0. So assuming that I'm going to assemble this 3-point charge here. I'm going to assemble this 3-point charge. So bringing the -1 nanocoulomb point charge is 0 because in a region, so in the initial region, there is no, as we will assume that there is no other point charge to be there. So -1 nanocoulomb is the first point charge to be assembled at this position 0, 0, 0. Now I'm bringing another point charge. I'm bringing another point charge 4 nanocoulomb to this point. Yep, to this point. So W2, I'm going to, I g- so the require, excuse me. So the require energy is Q times V1. So which is 4 nanocoulomb times the potential of this point charge. So the potential of this point charge is -1 nanocoulomb divided by 4 pi epsilon naught. So what is the distance here? Is 1. Yeah. So what about point charge 3? So I'm going to bring a point charge of 3 nanocoulomb to this position. So the energy required will be Q3 multiply V1 plus Q3 multiply V2. Um, V1 is still 1. So the distance from this to this, so the distance from this point to this point, or between these 2 points, is square root of 2. So we can calculate now. Okay, so total work done. Total work done is W1 plus W2 plus W3 is equals to 1.3368 times 10 to the power negative 8 joule. So it's 13.36, 13.37 nanojoule. Okay, so that's for example one. So using this involve a point charge distribution, discrete charge distribution. So I mean, it's up to you if you would like to do this using this formulation. I mean, I'm not a fan of. I mean, I'm not really a fan of memorizing formulas. So I mean, as I said, I will work. I mean, normally I will work through using I mean, the understanding. So which I have already explained to you how I arrive with all this calculation. Okay, moving on. So now we are going to look at, since we know um, what is the energy required, and also what is the force experienced by the charge distribution. So now we are going to look at some electrical properties of the conductor. So when we say material which is conductor, so normally the conductivity is greater than 1. Non-conductor or insulator, which is the conductivity is less than, very much less than 1. And semiconductor lies between, I mean, their conductivity lies between conductor and non-conductor. So at a certain excitation point, semiconductor can conduct electricity. So, but however, conductivity of metals generally increases with decreases in temperature, and of course it will the conductivity will decay as the temperature increases. Dielectric materials are normally non-conductor, or we call it insulator, because they they do not have the capability to electricity conduct electricity as conductor. So dielectric material, for example, what type of material that we have, like rubber, that is insulator, we call it insulator. Plastic is also one of the dielectric material. So anything which is not metal, not metal, are considered dielectric. So each of the material that we saw, that we seen in our eyes, even glass itself is a dielectric, material, because so at different different frequencies. So I'm talking about frequencies. So at different frequency, this material behavior, the characteristics are different. So they have different permittivity, and also at some point, some dielectric at higher frequency, they might have some conductivity. And for some conductor at higher frequency, they become an insulator, and so on. So so the material changes with frequencies, as well as also as temperature. So there are two different um, conduction of current. So electricity are generally related to um, conduction of current. So electric current, there are two types. One is convection, and another one is conduction. So the processes, I mean, this type of convection, current convection and current conduction is different. So current convection doesn't rely on uh, electrons charges. Okay, while current conduction relies on uh, charges like electrons. So the definition of current is rate of charge. The definition of current is rate of charge, which is dq over dt. And current density, again, the word density, it is always current divided by some dimension. And in this case, for current density, we normally associate with area, surface area. So the reason why is so how are we going to measure? So basically, how are we going to measure the current? So imagine that we have some kind of surface like this. We have a surface like this. We have some kind of cylinder surface, like we have a cylinder cross section like this. So the electrons are in motion, let's say, are in motion, passes through this surface. So the effective, how effective the what is the rate of charge that passes through this area? So we define how much of it we define as the current density. Okay. So therefore, we can also find that if, let's say, for certain material they have a certain current density, so that this current density is always depends on what type of metal um, that we use, or what type of metal that provide us. I mean that is going to provide a certain value of current density. So the current density could be constant. The current density could be a constant value, or is also dependent on space, in space. So there is, I mean, the direction of the current can be the, I mean, this direction of the current density here could relate to three-dimensional space XYZ. Okay. So the surface here, it depends on, and therefore the effective current through the surface, effective current through the surface, um, which depends on the requirement, where the current, I mean, where is the current that we want to measure. So if we want to evaluate the current at some surface, so it also depends that whether this current density is passing through the surface. So if the defined surface, if the defined, I mean the overall surface of interest does not does not effectively enclose the, I'm not saying enclose, so does not effectively being passed through by this current density, then the current, the evaluation of this current will be very small. So I've talked about convection of current, conduction of current. So convection of current does not involve uh, electrons, which in other words, it does not involve conductors. Conduction of current involve uh, electrons, the motion of charges, and displacement current density. Okay, so this part here we are not going to discuss, but this is more towards the dynamic field. So this displacement current density, this term here, is more towards dynamic the dynamic features. So that means this term, I mean this current density, will come into play when we consider time varying fields. So I mentioned before, time varying fields, that means the electric field varies with time, over time. So since we are not talking about dynamic features, so time time varying fields. So it's actually an important component. Actually an important component for Maxwell. Uh, that that is the key point. That is the key point. that enable the Maxwell equation holds. So this is the key point, actually, the displacement current. So again, I'm talking about time varying fields, the dynamic features. So we are not going to discuss this in detail. So as I said, the displacement current density, it is the key point um, uh, I mean, it's the key point for the Maxwell equation to hold. Okay, so convection current does not satisfy Ohm law, so it involves ion. So it involves the transport of ionized particle. So for example, like a filament. So now the definition of current is the rate of charge. So this charge here is basically represented by the ionized particle um, in a in a defined in a defined uh, geometry. Okay, in this defined geometry. So the volume charge, the volume, I mean the ions that contains in this volume. Okay, it is therefore rho v. So as we know, this is the volume charge density times the area that the ionized particle passes through, and the distance, okay, the distance that it passes through. So basically, so rho v, so charge, so this can be expressed, basically this can be expressed as rho v delta v, and delta v, and the differential volume is the surface multiply the length that the particle passes through. So here we can re-express the current, the total current that passes through the filament as in terms of the ionized particle velocity that this ion passes through the differential surface and multiply with the volume charge density. While conduction of current requires conductor, obeys Ohm law. So when an electric field is applied, then the force on an electron is, so assuming that there's an electron in a conductor. So when let's say we have both ends, let's say we have some kind of a conductor like this, a cylindrical conductor. So at both ends which is applied with different um, potential. So this electron will travel to the uh, will travel from high potential to from low potential to high potential. So normally positive charge travel from high potential to low potential. Electrons will travel from low potential to high potential. So if let's say the electron involves some kind of mass, right? So the force applied, it is mass times, so the force applied, it is actually mass times acceleration. So u is the drift velocity of the electrons. So the average drift velocity. So why is it called average? Because uh, the whole formulation here is hypothetical, because it is difficult to talk about the velocity of each electrons, because the electrons is going to collide with different uh, molecules in the or different atoms or different electrons in the conductor, right? So when the collision happens, so each of the electrons, they have different drift velocity. So therefore, the discussion here restrict to average. So we will take as an average because it, as I said, it is difficult to pinpoint of for each electrons what is their velocity and the time taken to reach and the time taken um, for the between the collision of the electrons between one from one interval to another interval. So therefore, the average keyword here is hypothetical. It's a hypothetical statement. So so force we know from Coulomb's law. So electron, the force on electrons is the electric field generated by two different potential, and the electrons experience the force, the electrostatic force, and then we would like to find what is the velocity here. So once we manage to find the velocity and the subsequent discussion um, that we're going to arrive is the Ohm's law, the current conduction. So we knew the current conduction is the volume charge density multiplied with velocity. Because bear in mind, the charge density is amperes per meter square, and the volume is actually in the dimension of coulomb per meter cube, and the velocity is meter per second, right? Meter per second, right? So this is the current. So coulomb per second is the dimension for current, which is ampere, divided by meter square. So coulomb per second is ampere. So the subsequent, as I said, the subsequent results that we are aiming for, um, whereby we want to obtain what is the velocity of the electrons under the influence of electric field in a conductor. So the subsequent results that we are trying to aim for is the Ohm's law at point form. So the implication is not direct, but we are going to look at the implication when we reach page 15. So we can see that the implication of Ohm's law. So I know we are already almost time here. So I will talk again with you tomorrow. Thank you everyone, and I apologize for some interruption just now because it's raining and it's just very loud just now. So I will talk to you tomorrow again. Thank you everyone.